In a multi-class classification problem, the goal is to figure out which class an input belongs to. To do this, we assign a probability to each class, showing how likely the input is to belong to that class. For example, if the input is a cat image, the model might classify it as a cat with 57% probability, a dog with 12%, a rat with 11%, and so on. To achieve this, we use the softmax function to map logits, which are the raw outputs of the model, into a probability distribution. The softmax ensures the output values lie between 0 and 1 and sum up to 1. To evaluate the model's performance, we compare the predicted probability distribution to the gold labels. In this case, we assume the classes are mutually exclusive, meaning the input can belong to only one class. The gold label vector is represented as a one-hot vector, where the value is 1 for the correct class, and all other entries are 0. Let us now focus on these two vectors, the predicted probabilities and the gold label vector. Specifically, let's concentrate on the value corresponding to the correct class. As you can see, if the predicted probability for the correct class is 0.57, it is slightly far from 1. This indicates an error. If this probability decreases further to 0.13, the error increases because the model incorrectly assigns a smaller probability to the correct class. On the other hand, if the predicted probability increases to a high value like 0.92, this is excellent. The error in this case must be very small. Let us compare these three cases side by side. For the first case, we need a function that indicates a small error. For the last case, the function must show a large error. If we multiply the corresponding values from the predicted probabilities and the gold labels, all zeros in the gold label vector will produce 0. The value corresponding to 1 will generate the final value. However, for the first case, this approach results in a large value, and for the last case, it produces a small value. This is not consistent with the required error representation. The solution is to transform large probabilities into small values and small probabilities into large values. This makes the values better representations of error. To achieve this transformation, we use the negative logarithm function. As you can see, the negative log maps large probabilities to small values, and small probabilities to large values. Assume the predicted probability vector is S, and the gold label vector is L. First, we convert S to minus log S. Then, we multiply the two vectors' element y's and compute their sum, as shown in this equation. By moving the negative sign outside, we arrive at the final equation for the cross-entropy loss.